Okay, we have a problem that involves somebody who leaves home and arrives someplace else 18 minutes later. The odometer in their car tells them that they've traveled a total of 12.0 kilometers, and we want to find the average speed. Now, this is an odometer reading, so this measures displacement along a path, not displacement from point to point, but a displacement along a path. And I'm going to use delta S for the displacement along the path, and we're going to distinguish that from what we get in part B in just a minute. Okay, understanding that this is displacement along a path and that our average velocity then will be in the direction that we happen to be traveling on the path at any instant, the average of our velocities will be delta S over delta T, obtained by the definition of average velocity as change in position divided by change in clock time. And we then put our change in position and change in clock time in, and we do the division. We get 0.667 for the number, and that's three significant figures, which is consistent with the three significant figures we have for both of our pieces of information, and it's kilometers over minutes, kilometers per minute. So average speed in this case, actually, the average velocity in the direction of our path is 0.667 kilometers per minute. Now, the second, we have a delta S, and I put an arrow over this. Okay, this delta S is what we call a vector delta S. It says that from beginning to end, our position changed by 10.3 kilometers in the direction 25 degrees southeast. So if north is here, east is here, 25 degrees southeast will be in this direction. This is a vector because it gives us how far and in what direction. A vector is a quantity that gives us a magnitude and a direction. So we have a magnitude of our displacement and the direction of our displacement. Okay, so our average velocity in this case is again rate of change in position with respect to clock time. In this case, the change in position is specified by magnitude and a direction. And we get our delta S over delta T, where delta S is 10.3 kilometers at 25 degrees southeast. That's divided by our 18 minutes. 10.3 kilometers divided by 18 minutes, I think comes out around 0.57 kilometers per minute. And it's in the direction 25 degrees to the southeast. So the direction is maintained. We divide our change in position, the magnitude of our change in position by change in clock time, and specify the same direction for our average velocity as for our change in position. Okay, in C, we want to know what the average speed is. Now, average speed is a whole lot like average velocity, and actually we calculated an average speed up here. We want the average speed for the entire trip if the distance each way was 12 meters. The average speed, which is the average velocity measured along the path, in the direction of the path. Okay, so the total distance we travel is 2 times 12 kilometers, and that's as measured by the odometer, or 24 kilometers. So our average speed is our distance divided by delta T, 24 kilometers. Now our delta T is 7.5 hours because this person leaves, arrives, apparently stays there for a while, and then comes back 7.5 hours after leaving. So the average speed during that, for that interval, for the 24 kilometers, was 24 kilometers divided by 7.5 hours, approximately 3 kilometers per hour. Average velocity, and the average velocity would be the vector delta S. Okay. And this is the difference between where we started and where we ended. Now, we started at the same place we ended. So ultimately, our delta S is 0. So we take the 0 displacement, divide by the 7.5 hour time interval, and we get an average velocity of 0.